Okay, geometry, we have kind of a long section ahead of us here. 12.2 is on chords and arcs. And chords are one of the vocabulary terms that we learned in 12.1 before. Arcs moves us into something new. So we've got several theorems to talk about here today. The first one right here, theorem 12.4, and there's a converse of it as well, says the following here, that within one circle or congruent circles, two central angles are going to be congruent if and only if they intercept congruent arcs. Now, if you remember that goofy phrase from back in chapter 2, if and only if is the telltale sign of what we call a biconditional statement. And what a biconditional statement means is that you can really read it in either direction. So we use that symbol there a lot. So a quick example of a biconditional would be something like, it is Christmas if and only if the date is December 25th. One of them tells you that the other one has to be true, and it doesn't matter which way you read it in either direction at all. So this theorem says that if we have one circle here, so we'll go ahead and try to draw that with our center right over here, we have two central angles that are going to be congruent if and only if they intercept congruent arcs. Now, a central angle is one that we defined back in chapter 10, I believe, if you talk about it at that point. And a central angle is simply formed by drawing two radii of a given circle right here. So if we do that, this right here is a central angle. And if you recall, we very often use the Greek letter theta as a variable here to represent an unknown angle. Well, this theorem tells us now that if we have a central angle right there and then another central angle, so let me switch colors now, and instead of blue, I'm going to do my second central angle here in purple. And let's see how carefully I can draw this. I want to try to draw a second central angle now that's congruent to the first one. So my hope would be that this angle is congruent to this one right here, and so I'll go ahead and call that one theta here as well. And this one says now that those two central angles are going to be congruent if and only if the arcs that they intercept are going to be congruent to each other as well. So when we talk about the degree measure of an arc, we're talking about how many degrees this arc right here and this arc right here are both going to be. And what we're going to find a little bit later is that whatever the degree measure of the central angle is in theta, this arc here is going to be exactly the same, theta degrees as well, and so is this one right over here. So the important thing here is, everybody, that if these two central angles here and here are congruent, then the arcs that they intercept have to be congruent as well. And we could also read that in the opposite direction because it's a biconditional statement. If we knew that the two arcs were congruent, then we could conclude that the two central angles would have to be congruent as well. Okay, so let's see that in an example right here, guys. Okay, so the theorem we just talked about said that you're going to have two arcs that will be congruent only if their central angles are congruent. Well, the two central angles that define these arcs, let's take a look. Here's the 5x plus 13 degree arc. That's intercepted or defined by this central angle right here. And the 8x minus 8 degree arc over here on the bottom left is defined by this angle here. Well, what hopefully you recognized right away is that with these two diameters cutting across, these are both central angles here, and they're also vertical angles, which means by definition, boy, the very first theorem we learned all year is that vertical angles have to be congruent. So we don't know the degree measure of these two arcs, but we do know that they're congruent. And the theorem we just learned, theorem 12.4, tells us that if these two central angles are congruent, then these arcs over here have to be congruent to each other as well. And once we figure that out, it's a relatively easy problem. So 8x minus 8, the measure of this arc over here, has to be equal to the 5x plus 13 up here on the top right. And then solving this should be pretty easy. We would subtract the 5x from both sides and get a 3x over here on the left. We would add that 8 over here to the right. 13 plus 8 is going to get us 21. Divide by 3 on both sides, and we're going to get x is equal to 7. And if we just wanted to verify that, it's never a bad idea to plug that in here. 8 times 7 is 56, and 56 minus 8 is going to get us a 48 degree arc right there. Top right, 5 times 7 is going to be 35 degrees, and 35 plus 13 is going to give us 48 degrees here as well. So, just like we hoped, we can see that those two arcs have to be congruent because we have two central angles that are vertical angles, and they have to be congruent to each other as well. Okay, second theorem we have on the day here is theorem 12.5. All right, within one circle or within two congruent circles here, two central angles are going to be congruent if and only if they have congruent chords. All right, so let's see what's going on right here. So we're going to draw ourselves, we'll deal with just the case with one circle right here. Okay, going to look something like that. Two central angles are going to be congruent if and only if they have congruent chords. So once more, we're going to try to draw a central angle, and I'll put one, kind of a big one here, up on the top. And then I'm going to draw another one, maybe somewhere off on kind of the bottom right here. So there's one. And there's one. Okay, and what we have here is a central angle formed right here, and another central angle we're hoping to be congruent right here. This theorem tells us that the only way those two central angles are going to be congruent is if the chords that they define, this one right here, and then this one right down here on the bottom, this is only going to work if those two chords are congruent to each other as well. Okay, so if these two central angles are congruent, then their two chords are going to be congruent, and vice versa. All right, let's take a look at what's happening in this example right over here. Again, no directions, but we're supposed to solve for x. So we've got a lot going on right here, guys. We are allowed to assume that this point right here is the center of our circle. Okay, and maybe the most important thing to take from this is the congruent chords that we have right here and right over here. Okay, now there are other segments within here. In fact, this is a radius, that's a radius, so is this, and so is this. So 4 radii are drawn within that circle, but then we have two chords that I've circled there that are congruent to each other. And again, back to theorem 12.5, it tells us right here, and again, remember, with if and only if, we can read this backwards right here. If two circles have congruent chords, then they've got to have congruent central angles. All right, well, in this circle, we do have two congruent chords, and that tells us that this central angle here, which defines this chord, and this central angle right here, which cuts off this chord, well, those two angles have to be congruent. The significance of that is that we know that this angle on the right is 6x plus 2 degrees. Well, the same thing is going to happen right here, 6x plus 2. And now if we take a look, we've got this angle at 6x plus 2 degrees, this angle at 6x plus 2 degrees, and a 44-degree angle in between them. If we look at adding all three of those angles together, we should realize that they form a straight line, which means they're going to add up to 180. So our equation here is going to be 6x plus 2 plus another 6x plus 2 plus that 44-degree angle in the middle, all told, has to equal 180 degrees. Let's combine some like terms. The 6x and the 6x is going to get us a 12x. The 44 and the 2 is going to make 48. All that is still 180. We're going to subtract the 48 from both sides right here and get 12x is equal to, let's see, that's going to be a 132 degree amount right there. Dividing by the 12 right there, I do believe that we are going to get x is equal to 11, and that should take care of that. Again, just a quick check now if you wanted to. 6 times 11 is 66 plus 2. That makes a 68 degree angle here. Same thing right over here. 68 and 68 makes 136. 136 plus 44 is going to get us the 180 that we were expecting to see for that half circle. Okay, let's move on to theorem 12.6, and here's another if and only if statement right here. So this is yet another one that we can read backwards because it's biconditional. This theorem tells us here that within one circle or congruent circles, two arcs are congruent if and only if they have congruent chords. So that sounds a lot like the last theorem here, but that one said that two central angles would be congruent if and only if they have congruent chords. This one now is talking about the arcs being congruent. So if we were to draw ourselves a circle, I think we're going to go with small central angles this time here. So I'm going to draw 1 and 2 radii over here on the right, and then maybe bottom left I'm going to draw 1 and 2 radii right over here. Okay, this tells us now that the arcs themselves are congruent to each other. So what we're talking about is the length of an arc that goes between these 2 points. Now the variable we usually use for arc length is a lowercase s, and we don't really do tick marks on arcs, so I'll go ahead and draw both of them and use the same variable to name the length of both of those arcs. So we'll use an S for both of them, indicating that they're the same. And this theorem tells us now that those arcs are only going to be congruent if, let's go purple right here, if the chords that they intercept are congruent as well. So if I were to draw a chord here in purple, and a chord, oh boy, a chord here in purple, those purple chords would have to be congruent in order for the arcs to be congruent to each other as well. So a lot of the same concepts are going on over and over again here. All right, let's take a look at what's going on in this problem. This is kind of an interesting one here. We have 2 chords that are drawn here. We have chord AD and chord BC. All right, and the theorem we just talked about told us that 2 chords, and it looks like their measurements here are 2x plus 7 and 4x minus 5. 2 chords would be congruent if and only if the arcs that they cut off would be congruent to each other as well. So we can see that this 2x plus 7 here on the left creates an arc right there of 100 degrees. What we don't know is the measure of the arc that's intercepted right here by chord BC, the 4x minus 5. But lucky for us, the chords that were drawn in this figure cut the circle up into a grand total of 4 arcs. We have arc AB, we have arc AD, we have arc DC, and then ultimately here we have arc BC. And out of those 4 arcs, we just so happen to know 3 of them, which means we can find the one missing arc pretty quickly and easily. 100 plus 100 is 200, plus a 60 is going to get us 260 degrees. We know that the total of all the arcs in any circle has to be 360. So if we take that 360, subtract the 260 that we know for the first 3 arcs, we know that this last arc, BC, has to be 100 degrees as well. And that's important now because we now know that arc AD and arc BC are congruent to each other. They have the same measure. Theorem 12.5, which we just learned then, tells us then that the 2 chords, 2x plus 7 and 4x minus 5, well then they have to be congruent to each other as well. So I'm going to write that out as a 4x minus 5 is equal to a 2x plus 7. Subtracting the 2x from both sides, we get a 2x on the left. Adding that 5, we're going to get a 12 here on the right. And dividing by 2, x is equal to 6. Plug it back in. 2 times 6 is going to be 12 plus 7. That's going to be a 19 right there. 4 times 6 is 24, and 24 minus 5 is going to be 19 here as well. So yeah, that one seems to check out. I like this problem a lot. This is one that a lot of people tend to look at and say, wait a minute, there's not enough information for me to solve this thing. But we've got to look a little bit more clearly at the diagram. So, looks like kind of a Led Zeppelin logo here, everybody. We have ourselves a triangle inscribed inside a circle. And the significant thing about that is that we've got 3 points located on the circle itself, and that creates 3 arcs on the circle. And together, those 3 arcs make up the entire circle. The other important thing is that it isn't just any triangle that's drawn inside this circle, it's an equilateral triangle because we have tick marks on all 3 of the sides right here. So that's pretty significant. In fact, I want to talk about that fact before we go any further here, guys. First of all, anytime you're dealing with an equilateral triangle, it has 3 congruent sides, but that also means that it has 3 congruent angles. So I'm hoping you guys remember this, but if this angle in this lower left-hand corner is B degrees, that means that all the other angles in this equilateral triangle have to be B degrees as well. And the 3 of those added together, B plus B plus B, which would be 3B, has to equal the sum of all of those interior angles in the triangle, which is 180 degrees. Divide both sides here by 3, and that's going to get us B is equal to 60. Now, I would think that some of you knew that already, and that's good if you did, because one thing we should take out of this year here, guys, is that every equilateral triangle is always going to have angle measures of 60, 60, and 60. No two ways about it. Now, the other thing to think about here is the fact that, as we said just a moment ago, we have three congruent chords here within this circle. And theorem 12.6, which we talked about a moment ago, said here that two arcs would be congruent if they have congruent chords. Well, we do have congruent chords, and this chord creates an arc whose degree measure is A. That means that the other chords also have to make arcs that are A degrees in each case right here. So when we look at the A and the A and the A, if we added those three together, that would have to equal the sum of all of the degrees of the arcs in the entire circle. And the entire circle is always going to add up to 360 degrees. Divide both sides here by 3, and that's going to tell us that A has to equal 120. Okay, so this is a long section here, guys. We still have a lot to go right here. I think I'm going to stop the video right now, and then we'll come back and we'll pick it up on slide number 8 in just a second with part 2.